Hello and welcome back to College Algebra, MAT 150. In this lecture we will be discussing optimization problems. So when you're talking about solving for quadratic equations, one of the types of things you can do is find the vertex or one of the coordinates of the vertex when you're dealing with word problems that involve quadratic equations. And one of the ways that we know that it's going to involve the vertex is the moment we see minimum or maximum or something along those lines. So when you see minimum or maximum, think vertex and think of the formulas that we have. So suppose we want to find all solutions for the following problems. Let's look at number one. H of t equals 8t minus 2t squared. So let h, given by this, be the height of the ball in feet t seconds after it is thrown. When does the ball reach its maximum height? So when does the ball reach a maximum height? We heard maximum. What do we think? Vertex. All right. So, and then what is the maximum height? So when does it reach the maximum height, and what is the maximum height? So when and what is the maximum height? All right. So again, what should we think? We should think vertex. So if h of t is given by 8t minus 2t squared, what is a, what is b, what is c? Well, the a is the number in front of t squared. And this is in the general form. So we're going to have to use the formula. So a is negative 2. B is the number next to the variable without a square, so it's 8. And then we don't have a c here. Not that it's useful in this particular instance anyways. But we, because of this, we're thinking vertex. We're like, okay, let's use this formula. X instead of x, it'll be t, rather. T equals negative b over 2a. B is 8. A is negative 2. So we have negative of 8, negative 8 over negative 4. Is positive 2. And what are the units here? So when does the ball reach its maximum height? So the when is sort of related to the x coordinate, or in this case the t coordinate, and it's given in seconds, so 2 seconds. So in 2 seconds the ball reaches its maximum height. And we know it's a max height because what is the a value? It's negative. So that double confirms that what we're asking for is legitimate in this case. If it was positive, this wouldn't make sense. All right. So further, we found the when. So we're good there. Now we need to find the what part. So the what is the actual height, and that's given by this. So we have to plug 2 back in. So h of 2. It's given by 8 times 2 minus 2 times 2 squared, which is equal to 8 times 2 is 16. That's one term. Minus 2, remember you square first, then multiply. So 2 because of order of operations. 2 squared is 4. And then 16 minus 2 times 4 minus 8. That's 8. So what is the maximum height of the ball? It's 8. Let's give it some context. 8 miles, 8 light years? No, it's 8 feet. Okay, and what is 8 feet is the maximum height of the ball. So units are important, but also giving context to what's going on is usually a pretty good idea too. All right, so that's for something like this. Sometimes these problems don't just have the formula already, or rather the function kind of already given to you. You might have to actually develop it yourself, and that can be a little tricky. So let's start with a somewhat easy one to actually develop the equations for. So what if we're trying to find two numbers? Okay, two numbers whose sum is 50, and then it says have the largest possible product. That's pretty pretty condensed question there, or condensed problem. So, so we're looking for two numbers. I'm going to call them x and y. You can call them whatever you want. But a good idea when you're doing a word problem is to define variables, especially when you have to make the equations or functions yourself. But let x be a first number, and let y be a second number. Could be different, could be the same, it doesn't say. But it says their sum is 50. So a couple things. When you hear sum, you should think add. So find two numbers whose sum, so the two numbers whose sum, you add them up. And then it says is 50. So when you hear is, think equals. So x plus y equals 50. So that's one equation. And then it says have the largest possible product. So this is where it gets interesting. So what's the largest possible product? Well, when we say product, we're thinking multiplication, and we're thinking about the multiplication of them. So we want x times y to be as big as possible. So I'm going to call this a function. I'm going to call p the product. Now we don't care about actually finding how big the product is. We just need to find the two numbers that give us the biggest product, which is interesting in its own right. All right, so this is kind of our function. But here we have x plus y equals 50, p equals x times y. Well, we don't know how to find the largest or smallest. We got two variables. Here we have three variables if you consider p to be a variable, which it is. But we do know how to deal with it when we have x or y or something on one side, and then we have a single variable throughout on the other. So we use this idea of this x plus y, which is called a constraint. Constrains how big or small the x's and y's can get relative to each other. So, and then we can basically, this constraint will restrain what these two things are. So I'm going to solve for y by subtracting x. And we're going to do this so that we can whittle this part down to just having one variable on one side, which is what we want. We don't know how to deal with it like this, but when we have that one variable on one side, we do. All right? So y equals 50 minus x. So what do we do with this constraint about constraint on y? Well, we can plug it in to y. So instead of plugging in like 2 or 3, we just plug in 50 minus x. It's like the compositions that we dealt with earlier. So again, still not a form that we know, but if we distribute the x, we get p equals 50 x minus x squared. Now we have something on one side with just one variable. And then we have p equals. So we're trying to, and what does it say we want to do? We want to find the largest. We want to maximize. So when we hear this, we should immediately think vertex. So vertex, this is the input, that's the output. That's the thing we're trying to maximize. So what is the vertex given by? Well, x equals negative b over 2a. This is the formula for the first part that we had to always find. And what is a? Again, a is the one next to the x squared, so it's negative 1. And what's the b? The b is the coefficient next to the x, so in this case it's 50. So again, don't forget the negatives for your coefficients. So we have negative of 50 over 2 times negative 1, which is negative 50 over 2 times negative 1 is negative 2, which is positive 25. All right? So we have positive 25. And again, what does it want us to find? Two numbers whose sum is 50 that have the largest possible product. Well, here, does it ask us for what the largest possible product is? It does not. So we don't have to actually take this and plug it, we don't actually have to take this and plug it back in like we're used to. We're actually trying to find, we found the first number, let's try to find the second number. And we have a formula that relates the first and the second number. So now we can take this and plug it back in. 50 minus 25, well, that's just 25. So the first and the second number are exactly the same. And the two numbers, do they add to 50? They do, 25 plus 25. And apparently the biggest possible product is just 25 times 25, which is 625 for those who are curious. All right. So that's one way that word problems can kind of pop up. Let's take another look at another example. So if we have a landscaper, so a landscaper has enough stone to enclose a rectangular koi pond next to an existing garden with 24 feet of stone wall. If the garden wall forms one side of a rectangle, what is the maximum area the landscaper can enclose? What dimensions of the koi pond will yield this area? So there's a lot of things to keep track of. So we're trying to build a koi pond that's rectangular. So let's just start with that. Let's draw a picture, if you can, to see what we can get out. And the previous one, we couldn't really draw a picture, but if you can, it's a good idea. Money problems, direct math problems, stuff like that don't usually work, but problems like this that have an application, have some sort of geometry, are really good problems to go ahead and try to draw. So it says, so rectangular koi pond next to an existing wall with 24 feet of stone wall. If the garden wall forms one side of a rectangle, what is the maximum area of the landscape? So this is kind of a crucial thing here. The garden wall forms one side of the rectangle. So this means that what we're actually concerned with, so we're trying to find out what, with the 24 feet of stone wall that we have, if we put basically three sides next to an existing wall, what will this form? Well, so what do we know? Let's call this the width and this the length. So how much stone wall can I possibly use? Well, I have a W and another W, so that's 2W, plus another length. All of that together should equal 24 feet stone wall. All right? And what are we trying to optimize? We're looking to maximize the area, so we want to make this as big as possible. Well, what is area for a rectangle? Well, area is given by length times width. Okay? So W is the length in feet, or W is the is the width in feet, excuse me. And L is the length in feet. See if we can get this right this time. All right. And then, so we've defined our variables. Usually that is a really good, again, I can't stress that enough, a really good idea is to, when you're dealing with variables, define them. Even this, we'll say A is the area of the koi pond. And this is width of, in feet of the koi pond and length in feet in the koi pond. So we have all these defined, and we have a constraint. So again, the two variables are what we call our constraint. And we're going to do something we did last time. So we're going to solve for one of the variables, L. So subtract 2W from both sides. So if we have 2W plus L equals 24, subtract 2W, we have L equals 24 minus 2W. And this means that our area function is given by 24 minus 2W times W. And to come back to make sure we're on the same page, what are we trying to maximize? We're trying to maximize the area of the landscape. So that's what we want to actually take that, find the vertex of, with the A function there. And that means that we need to have this side to be nothing but one variable. That's how we know how to take a vertex. So that's how we knew we had to manipulate this one to plug into that one. All right, so we have 24W, so we'll distribute the W here, minus 2W squared. And now this is something we can take, or we can look for the vertex of. A is what? It's -2. And what is B? It's 24. Remember, A is next to the squared term, or next to the squared variable, and 24 is next to the variable that does not have an exponent other than 1. So, W, that's our variable, so W equals negative B over 2A. Again, that's what when you're doing the vertex, it would always be of whatever variable you're using. Negative B, which B is 24, over 2A. A is negative 2. So we have negative 24 over negative 4. And what does that equal? Well, that equals 6. Okay? And this is an interesting thing to note here. Do we need to put feet next to this? No, because we clearly define what width is. Width is in feet. So because of that, we are not required to put units there because we've already discussed units. All right, so let's go back. So what is the maximum area that the landscaper can enclose? Well, we found the x-coordinate. Does that actually tell us? No. What we need are, before we do anything else, we need to actually plug this in and actually find what the maximum area is. So it didn't say what is the width for the maximum area, what is the length. So the maximum area is 24 times 6 minus 2 times 6 squared. Actually, yeah, we'll just come to the right. 6 times 24, that's 48. 72, that's 144. Minus 6 squared is 36, minus times negative 2 is 36 is 72. So 144 minus 72 is 72. And this one, we didn't actually, I put the area of the koi pond, and if we actually put areas in feet squared, we don't have to put it there. But if we didn't, we would have had to put feet squared. So I went back up there and put that in our definition. So area is in, so the area is 72 feet squared. All right, so we found the area. Now let's look at the next. So what's the maximum area that the landscaper can enclose? We're done with that. And what dimensions of the koi pond will yield this area? So we found the length, right? So or rather, we found the width. That's 6. To find the length, we can just plug it back into this. So length is 24 minus 2 times 6. 2 times 6 is negative 2 times negative 6 is negative 12. And 24 minus 12 is 12. So the length is 12 feet. So we've answered, so the length and width are the dimensions of the pond, and area is, and the area is found, so we are done with this problem. That concludes this lecture.